Okay, let's pick this up from yesterday. Um, Before you watch this, you should have watched the two Castle Rock um, videos on um, practice problems. There's actually at least a third one that if you wanted to watch that would be good as well. But I hope that you did do that. Um, if you haven't, that's fine. Watch them immediately after this, and it'll help you with other practice problems. So last day we looked at practice problem, doing the practice problem 6.3.1 and the quick check 6.3.1. So let me grab paper and we will look at least one of each. So practice problem 6.3.1, that's on page 245. And so it says draw a circuit showing a 6-volt battery, internal resistance of 0.5 ohms connected to a parallel network consisting of a 25 ohm resistor in parallel with a 6.25 resistor. So it's just saying, okay, you've got a 6-volt battery, 6.0 volts, and with an internal resistance, so we're going to put an internal resistance here of 0.50 ohms, and so this is the battery, like this, and in series with a parallel network consisting of two resistors, and one of these is 25 ohms and the other one is 6.25 ohms, like that. And then it says calculate the current of the battery. Okay, so the first thing you need to do is we need to go back and we need to find out what the so that what this is A, we've done A. So we need to find out first of all what the resistance of this is. Okay, so the resistance 1 over RT is equal to 1 over 6.25 plus 1 over, oh, you can't see this, sorry, 1 over 25 ohms, and these are all ohms. And this comes out to, if you do, I'm not going to go through the whole thing, but if you do this, it's eventually going to come out to 5.0 ohms. So this whole thing over here is 5.0 ohms. Okay? The current is going to equal voltage divided by resistance, which is equal to the 6.0 volts, and the resistance is going to be this resistance plus this resistance. So 5.0 ohms plus 0.50 ohms, and so if you do the math, this ends up coming out to 1.1 amp. Okay, pretty straightforward. Okay, the next ones are pretty much the same as that, just using 1 over finding 1 over RT is equal to 1 over R1 plus 1 over R2. The only difference is that where you get 2, like if you look at this one here, if you look at B here, you have to add those two together first, and then use 1 over these two. Okay? So this would be 1 over this total plus 1 over this total is going to be 1 over the net resistance. Okay? This is kind of like fun. This is kind of like fun stuff. If you have any problem with that, give me a shout. Okay, so that was sample problem, or practice problem 6.3.1. Quick check 6.3.1 is more of the same pretty much. I'll look at one of them anyway. So here we have, in this case here, we've got 1, 2, 3, 4, 5. So 0.5 ohms. Okay, now this is a little bit tricky because 1 over 0.5 ohms is going to be 2 plus 2 plus 2 plus 2, so it's, look at 8. Okay, so it's going to be a bit different. So if we look at number one in quick check 6.3.1, so this is quick check 6.3.1, and this is on page 246. So number 1. So 1 over RT, call it, is going to be 1 over 0.5 plus 1 over 0.5 plus 1 over 0.5. How many of them are there? 1, 2, 3, 4, 5. There's 5. Plus 1 over 0.5 plus 1 over 0.5. And so 1 over RT is equal to, turns out to be 10 ohms. Okay? So if that if 1 over RP is 10 ohms, then the inverse of this, so RP is going to equal 0.1 ohms. Okay? So the net resistance is going to equal RT from this whole, I should call it RP of the parallel, plus the internal resistance. This is equal to 0.1 ohms, and the internal resistance is also 0.1 ohms. So net is going to be 0.2 ohms. And if I plug that into Ohm's law, where the current is equal to volts divided by, volts divided by resistance is equal to 1.2 volts divided by 0.2 ohms. So the current now is 6.0 amps. Okay? So Bob's your uncle. Alright? So we'll do that one. The other ones, I think one of the other ones has got a QR code, right? Yeah, 4's got a QR code to begin with. So that's pretty straightforward. The trick with 4 though is because it's so convoluted. I'm going to show you my solution, but I'm not good. I'm not good with those funky cross the diagonal diagrams. This stuff just bothers the heck out of me. So what I have to do is I actually have to revisualize this. And if you revisualize this, it's like this. There is a 2 amp. I'll show you this one. This one's a bit more. If you redraw it, and remember these are just wires, so you can add on to wires and all that kind of stuff. So we need to rethink what this looks like. So when I rethink what this looks like, it comes out to this. Okay, all of this whole thing is in here. Okay, so 6 is here. There's the 6 and the 12. So it's kind of like a weirdness, I know, but if you redo it this way, then all of a sudden this is easy. So you have this is in parallel, so you find out what the overall is. Then now these two are in series, but these two together. So these two in series, there's 4 ohms and 2 ohms. So now this 6 and this 6 is in parallel. Okay, so now you have to find, so 1.6, so that's going to be 1.6 or 1.6 is it turns out to be 3. Okay, and then 3 ohms plus 3 ohms in series now is 6 ohms. And so the 6 volts divided by the 6 ohms is 1 amp. Yeah. Maybe pause and either take a picture or try to rationalize this with what you see on the page. And it'll take a bit, but I'm pretty sure that it'll make a little bit more sense when you're done. Okay, so that's it for me now. And from here, if you have not completed the Kirchhoff's laws, practice problems, and the videos, do that. And then today, I want you to look at this. So what's up now? Oh, have to fill in the notes. Duh. Actually, one of the videos does this for you, but I will do this for you now anyway, just to finish this off. The Kirchhoff's laws of current and voltage are pretty much worded the same, and their advantage is the same. Kirchhoff's law of rule says that at any junction in a circuit, the sum of all currents entering that junction equals the sum of all currents leaving that junction. Sum of all, currents leaving that junction. So what does that mean? That means, say here's a junction here. Here's a wire going in, wire going out, wire going here. Let's say the current here is equal to 6. Now let's say 6 amps. Let's say the current leaving here is 4 amps. That means the current leaving here is equal to 2 amps. Basically, that's all it means. So it's additive. Okay? Kirchhoff's voltage rule is that the algebraic sum of all the changes around a closed path in a circuit is 0. What does that mean? Well, basically it means something like this. Let's say you have a voltage over this battery that is, say, 6 volts. And let's say this thing goes out and there is, say, two resistors in it. Okay? And if this is 6 volts, and let's say that the voltage drop because of resistance here is 4 volts here, that means the voltage drop over here is going to be 2 volts. Okay? Because the algebraic sum of these has to equal to 0. Okay? And that's it. So on the books today, review 6.3, and I'm going to look at those right now, and I'm going to prescribe something to you. 6.3 has a total of 9 questions in it. I'm going to give you an extra day on this, and then I'm going to give you, I think, another 2 days on the Chapter 6 review. Okay, I've made up my mind. Okay, so for next day, do the first half of the Chapter 6 review. 1, 2, 3. Yeah. Do the first 5? No. Okay. Do the first 4. No, do the verse 3. Because we've used a lot of time today. So do the first 3. Next day we're going to do the remaining 6. Day after that we're going to do the first half of the chapter review, and then which is a lot. We're going to be doing a lot of work, and then because there's 26 questions, and then the second day, the fourth day, the last half. Okay? So, love you. If you need help, you know where to get me. Let's rock and roll. Love you. Go away.